Okay team, I'm Maddie, welcome to Science Side Up, and today we are still talking about the first law of thermodynamics. Oh my gosh, we've got this far and I haven't even had to resort to calculus. So that's this form. Now we're gonna get into some other forms of this equation that are very useful. So let me erase this and then we'll jump into stuff. Okay team, here's our original equation and now we're going to do two things to it. One, I'm going to rearrange it so that it's in terms of Q, and then I'm gonna rewrite it so that we're thinking about all of these terms as a change. I rewrote everything in terms of a change because now we're gonna start thinking about closed systems. So a closed system is one that everything about that system, everything that can possibly interact with it is inside the system. So we don't let outside energy come in. All we can do is move the energy around inside the system. And we do that because that's a nice theoretical framework to think about these thermodynamic problems. The next thing I'm gonna do is I'm gonna divide each of these terms by mass. The reason that I am doing that is because, believe it or not, it makes the math way easier, and two, that's a pretty standard thing to do. That's kind of more normal to handle thermodynamics problems. Notice that now instead of drawing triangles, I wrote the lowercase letter d. In calculus, both the lowercase letter d and this triangle, the capital Greek letter delta, can be read in English as the word change. So both of these terms are read as the change in heat, or the change in heating. The triangle you typically use for a discrete system, whereas a d you use when you're referring to the derivative of a continuous system, but conceptually they represent the same thing. Second, notice that I switched from uppercase to lowercase letters. That's a standard thing in thermo. Once you divide through by mass, we're talking about specific values. That word specific in thermodynamics just means I divided this term by mass. And then we write it as a lowercase instead of an uppercase. So a lowercase letter, that variable has been divided by mass. Uppercase, it has not. Okay, so this is still my change in heating equals the change in internal energy plus this like change in work. Now we've got to think about that work term. And I'm gonna immediately erase that lowercase w because, believe it or not, in thermodynamics, a lowercase w means a different variable. So I don't want to confuse anybody, but I did want to show that we're bringing this work term down. So I'm going to write this as this work term as pressure times the change in specific volume. Specific volume is volume divided by mass, and it is represented by the Greek letter alpha. So let's pull apart this term really fast. I'm gonna get a different color chalk. Work is equal to a force times distance. I'm gonna use the letter x to represent distance because we've got d's all over the place. So force here has, well, units of force, that's a Newton typically. So this is newtons times length, which is meters. Now, pressure has units of force per area, which is gonna have units of meters squared. Sorry, that should be an N for newtons. If I take pressure times volume, I end up with units of newtons per meter squared times meters cubed, which is newtons times meters, which is happy day units of work. So pressure times volume is going to have units of work, but then when I divide it through by mass, I end up with specific volume to make my units here match these guys. I am making an assumption in this form of the equation, and that is I am allowing volume of a system to change, but I'm holding its pressure constant. Generally, when you're doing a first law of thermodynamics problem, we're going to think of it as either pressure is constant or volume is constant, and generally we don't let both of those things vary at the same time. You're gonna see why that's important as we keep moving forward.
Hey team, editing Maddie jumping in here. I think we're gonna break this video here because it's already almost 6 minutes. So that is the first form of the first law of thermodynamics equation. This is going to be one of the most common forms that we use moving forward. So in the next video, we're going to get to the second and hopefully the third form of this equation. So be looking for that one here in the next couple days. All right, awesome. Thanks team.
Yeah. This is going so well.